Okay, here is hopefully what will be a somewhat quick video, which for us is lesson 7. Okay, in title of the lesson, I don't remember it. I think it's something like 2D and 3D motion in calculus. But there's the concept of a vector valued function that's part of that. Okay, so what's a vector valued function? Take something like what you're looking at right here. The input is t, which is a scalar, and we could call that the parameter if we wanted to. And then once you put t in and you do the calculation, you get out r of t, which is a vector. So that's why we call it a vector valued function. And this vector is 2-dimensional. You could have 3-dimensional. If you can imagine it, you can have a 4-dimensional vector, and the sky's the limit from there. Okay? All right. Now, let's put on top of this a scenario. All right? So we'll say that take that same vector value function. T will be time, and r of t will be the position vector at time t. The position vector just being a vector that indicates the position of an object at a time. Okay? And the question, I think this is the first question on the lesson, says that we'll have that on the interval from 0 to 5 for t. Now you can think of that as like the clock. The clock runs, it starts at t is 0, and you get all these increments of time up until t is equal to 5. Okay? All right, so here's what we want to do about that. 2 parts of the question says, can you find the path of this moving object? Every moving object moves along a path. Okay? And B, can you use a table to sketch r of t and its path? All right? Now, how about this? Let's try to do B before we do A, even though it makes sense to do A before B. All right? Anyway, so it says use a table, and of course, we would have to use times that are within the clock that's running on this moving object. So I don't know, it's like you could do like 0, 2, and 5. Okay? So say you put the scalar t in 0 into there, you get the vector 1 and 2. And then say you put 2 in, you would get 3 and 0. And then say you put 5 in, you would get 6 and -3. Okay? Just by direct substitution. Now, I'm going to draw this in a way where I really want you to get a feel for the position vector being a vector. All right? I think that'll be important as we go further along and we try to understand and learn more about this. All right? I'm going to try to make a little scale here in a graph and so on. So here's what we get. R of 0 is the vector 1 and 2, which take me right there. It says you're right there when t is 0, but there's a vector that indicates that position. Now you might say, what's the point in using a vector to indicate the position? Well, we'll develop that as we go along. Okay? But there's r of 0, putting you at position 1 for x, 2 for y. And then later we found when t is 2, it puts you at 3 and 0. Okay? So like right there. Now, that's the spot that the object is. That's its location. That's its position when t is equal to 2. But there's a vector, right? And I don't want you to take the vector for granted. All right, so I'm going to draw that so that you don't take it for granted. That vector there in red, that would be r of 2. And one more, r of 5, 6 and -3. So if you went right 6 and you went down 3, you'd be about right there. And so when t is equal to 5, this is in fact the position that you occupy. But again, as I keep saying, don't forget that there's a vector that's indicating that that's your position. Even though you might think that that's silly at this point, that we need a vector to indicate a position. You say, we just put a point. Why don't we just put a point? And I have to say, well, you'll see as we develop this topic why we need to indicate the position of a moving object by a vector. Okay, even though it might seem silly now, we do need to represent the position by a vector. Anyway, now it could be a little hard to tell the path if that's all you did. I mean, as I tried to draw a pretty nice graph, it looks like the path is linear. But, you know, I mean, I guess these 3 points, they don't prove that it's linear. Okay? So that's why that we might do this, and I might show you this so you get a concept of t being a scalar, t representing time, r of t being a vector representing the position. But then there's this whole path that's imposed on that, okay? Because a moving object would have a path. So let's maybe get A and B to work together, all right? So here goes. Let's go back to A now. Say, what's the path? Now, the path, if I give you a definition, it would just be information about x and y. So, in other words, it would eliminate the time element out of it. So you can imagine that, you know, maybe somebody walks somewhere, okay? And maybe they walk fast or slow, and depending on if they walk fast or slow, time would have to be involved, right? I mean, because there's no concepts of fast or slow if there's not a concept of time. But what if you just talked about the path that they walked on? Well, the information about the path, like the actual footsteps, would totally leave out the concept of time. So if you can take r of t right there and somehow eliminate t and just give me information about x and y, well, I mean, on the xy plane, that would just be the path, okay? So how would you do that? Well, the way you do that is we try to take what we see here that has t in it, and we introduce x and y somehow. So we'll say all r of t seems to say about the position is that in general, x is found by 1 plus t, and y is found by 2 minus t. Okay? And then we try to eliminate t out of this. Now, you could have, like, just the way it is, we don't really even have to do anything this time. You can eliminate t by substituting one of these into the other. You can eliminate t by adding these equations together. T will cancel right out of it. We'll get x plus y is equal to 3. And if you really want the explicit equation of a line, we'll say y is equal to 3 minus x, okay? So the path, you know, which has nothing to do with time, the path would give no information about speed, for example, because time is left out of that altogether. The path, or the footsteps, or whatever you want to call it, is that line, and you can see that looks about right. A line that has a slope of -1 and hits the y-axis right here at 3. So I thought I was hurrying my graph, but I guess it worked out to be pretty good. So here we go. In pencil there is the path as indicated by the position vectors from my table. Okay. All right. So let's say, like, as far as answers, like, there's the answer to A, the path, and then here's the answer to part B, which is to give a little sketch about what the motion would look like. Now, another thing that we do is, if we say, well, in pencil there's the actual path, and then you can get a little bit of a feel for the speed of the object, because I guess you could say it took 2 seconds to get from here to here, and it took 3 seconds to get from here to here, right? Because that's 0, 2, 5. But what we'll do is we'll say that here's the direction. We might put some arrows on it and say that, all right, not only is that the path, but it was moving like so. Okay? All right. So through that first example is an easy example. None of the math is hard. The point of it is you get the concepts of, you know, looking at something like that, seeing that it gives you the position at a given time. If something's moving, there's the concept of the path, there's the concept of the positions and the times, and it all comes together in one picture. Okay. All right. Now, next example. Okay. Let's try do the same thing with this. Objects moving according to r of t is cosine t negative sine t, and the clock runs for like 6 seconds. Okay, from 0 to 2 pi. That's how I'm going to read that. 2 pi is about 6. So let's try to do b first, just to show you that it's really hard to get an idea of what the motion looks like if you just plotted some positions out of that. All right. So here's what I'm going to do. I'm going to draw a grid, and I'm going to ask that you imagine that I'm making a little table along with it, and I'm going to let you do the math and prove that I'm right. But instead of me actually making a table, I'm going to just make the table in my head, and I'm going to plot the vector. So look at that. What if t was 0? The clock does start at 0. What's your position vector? Say you put 0 for t, you would get cosine 0 sine 0. That would be the vector 1 for x, 0 for y. Puts you right here. Okay, so like right there. So there's r of 0 being 1 and 0. Okay. Now I guess I could choose like whatever span of times I want from 0 to 2 pi. I'm going to choose times that are within that are easy to calculate. So, I don't know. I might do, how about pi over 2? So what happens when t is pi over 2? Cosine pi over 2 is 0. Sine pi over 2 is 1, but I got negative sine. So that's going to take me down here. Okay. So you start off here, and then I guess you could say at about 1.5 seconds later, you end up down there. Now, I don't know how you get from here to there, but you start here, and then that amount of time later, you end up over there. Now, to keep going, this will be r of pi. That's going to be my position vector, 3 seconds into this, which is still about 1.5 seconds after that. R of pi is equal to negative 1 for x, 0 for y. Position vector, a vector indicating the position at that time when t is pi. And then finally, I'll do 3 pi over 2, and you can double check my math, and you'll get that r of 3 pi over 2 is 0 and 1. Okay, so what all that tells us is that you start here, and then pi over 2 seconds later, you're here. And then pi over 2 seconds after that, you're here. And then pi over 2 seconds after that, you're here. It doesn't tell us how. It doesn't tell us the path. If I'm going to be dramatic, I could say, you start here, and maybe, who knows, you went like this, and at that moment, pi over 2, yeah, you ended up right there, okay? Now, we think that's probably not what happened, but, I guess it's possible. If all you know is you start here, and then later you're here, it doesn't tell you what happened in between, okay? So, all right, fine. Doesn't tell you what happened in between. That's why we might try to find the path. Okay, so how do we find the path? The path would be just information about x and y. It would eliminate the concept of time completely out of this. Okay, so I'm going to say, all right, I want information about x and y, and I want to eliminate time, t, out of it. I have to start by saying that. Isn't this how the position vector indicates the position? The position being a point, x and y. Okay, sure. And then I have this idea about how we can eliminate t. Say you squared both sides of that, and say you squared both sides of that, which you can do that if you want to. It's going to say x squared is equal to cosine squared, and y squared is going to be sine squared, given that the negative 1 will square out of it to be positive 1. Okay, now I know that when you add cosine squared and sine squared, you get 1, And if they're linked directly to x squared and y squared, then when you add those, you have to get 1. So my path is going to be x squared plus y squared is 1. Okay? All right. So there's the path. So the path is, in other words, circular. Okay? All right. Now, I guess now I can see that. I drew this like squiggly line to say, who's to say that you didn't get from here to there on that squiggly path? Well, now I can tell you that that's not what happened, because the path of getting from here to here or anywhere must be along that circle that has a radius of 1 and a center at the origin. Now it's going to kill me to have to draw a circle. I don't have my circle template. This is the ugliest looking. This bothers me so much. Anyway, but there, okay, that's what the motion looks like. What's the direction? You start here at 0. At a slightly later time, you end up over here. So you're moving, if you just follow the progression of time, you're moving clockwise, okay? All right, clockwise motion. If I was going to describe this, I would say clockwise motion around a circle that has a radius of 1. Okay, that's what motion according to this is. Now, another thing we can say about this. Does it look like the speed might be constant? I mean, from what I have here, as far as I've taken it, I can't prove that the speed is constant, but doesn't it look like it is? Because how long did it take you to get from here to here? Pi over 2 seconds. And then how long did it take you to get from here to here? Well, from this time to that time, that's also pi over 2 seconds. It looks like you're covering equal distances in equal times. And that's what constant speed would be. Now, I'm gonna say that it looks like constant speed. Okay, it certainly seems like that because we're covering equal distances in equal times, but you know, I don't have any information, even though I know it's a circular path, whether there was some speeding up and slowing down and coincidentally landing on those spots. You know, as far as I've taken, I can't prove that. All right, but okay. So to move according to this, with the clock running like that, puts you on a circular path, radius 1, center at the origin, clockwise. All right, starting here and ending up right back where you started. Okay, I didn't do it, but what's r of 2 pi? R of 2 pi when the clock stops is also 1, 0. So we'll say something like this. Motion is clockwise and 1 revolution. 1 trip around that circle. That's what we get. Okay. All right. Now, so first two examples, they should look a lot alike. That's the idea. Next one I want to do is what I think is example 5 or problem 5 in the lesson. And it says this, that we have an object in motion. Units will come into play at this point. Distances will be in feet. Time will be in seconds. And I give you an initial position and a final position. Okay. And we'll just say that, you know, who knows exactly what path you're moving on or how you're doing this, but you start here and 3 seconds later you end up there. Okay. Can you find the displacement vector? Now, we talked about this a little bit when we had the first test. Okay. So, you know, this I hope would be review, but if it's worth saying again. Okay, so I'm going to draw this out. I'm going to write some equations. Okay, so let's say you start at 5, 1. All right, 5, 1. That's going to put you here. Okay, now I'm going to put the vectors in red because I want to make sure that that concept stands out to you. But there it is, R1 is 5 and 1. And then some later time, you find yourself at 2 and 7, which will be here, okay? So there's r of 2. Okay. It take you 3 seconds to get from here to there. What path? We have no way to know. There's absolutely, in this problem, no way to know how you got from here to there. But if we know that you move from one spot to another, even if we don't know how, there's this concept of displacement, which is a vector that comes up, okay? And so I would say, like, it's real simple, actually. The displacement is how you get from your initial position to your final position. So you could say, like, all right, look, if you were going to go from here to there, that's how you know, with this, that's how you'd go. That's how you get there, okay? Even though we don't know the exact path or how you might have gotten from here to there, that's what the displacement is. So we'll say D for displacement. What are the equations? Remember for test 1, we talked about how you add vectors geometrically. Here's how I could interpret this in terms of geometric vector addition. It looks like you take R1, your initial position, you add that displacement vector, and you end up with R2. So I can say there's one equation that involves the displacement vector. A flip side of this is you could say that displacement was the final position minus the initial position. So those are the equations that govern how this works out. Okay? All right. Anyway, so find the displacement vector. Well, they're your equations. I guess it's your choice how you want to use it. I mean, I think if I want the displacement vector and that's what I had, then I would use the second one, even though the first one is still operative. So, okay, we'll say do 2, 7, and subtract the vector 5, 1. Okay? And then we'll find that the displacement vector is -3, 6, which just means that according to starting here and ending up there, we would have to go left 3 and up 6, which certainly looks correct. Okay? All right. And I guess if we wanted to give units to the displacement vector be in feet. Okay, because say we measure all the distances in feet. All right. Next thing, the average velocity vector. Okay, so here's a concept then. All right, it might be a new one for us. But we'll say velocity is a vector. And for me to give you the average velocity would be to give you the displacement vector over the time that elapsed to get from the initial to the final. All right. Okay, so I could go back to my first slide and use it. Why do we have to represent the position by a vector? Well, because basically, I mean, if you're going to explain what velocity is, it's going to have to be a vector too. And it's determined from the position vectors. You subtract 2 vectors, you get another one called displacement. Velocity will be basically displacement over time. Okay. All right, so we're going to take -3, 6, which is our displacement. And how much time passed it? It's 3 seconds. So we're going to divide that by the scalar 3. Now, there are units here. Displacement is going to be in feet, and time will be in seconds. So we'll say dividing this vector by that scalar, -1, 2 is the velocity vector, and it's in feet per second. Okay? All right. Basically says that to get from here to there, you'd have to move in the direction left 1 up 2 with units of feet per second. Okay. Average speed. Now, a new concept. The average speed is just, I guess if the velocity vector told you something, it told you the direction you're moving, which is in the direction of left 1 up 2, which is basically the direction of that. And it would also tell you how fast you were moving in terms of distance over time. So the average speed will just be the magnitude of the average velocity vector. Okay? So we'll say, okay, that'd be, see that vector right there? It's the square root of 5. Okay? square root of 5 feet per second. Now that's not a vector. The speed, being the magnitude of velocity, is a scalar, okay? The velocity is a vector. Displacement is a vector. Position is a vector. But the speed, all right, we're moving left 1 up 2 at a speed on an average terms of, like 2 point something feet per second, all right? So that's what that all tells us. All right, so now to impose everything on the same picture, I would like you to see this. I'd like you to see that, okay, there's your initial position, there's your final position, there's your displacement. How does the velocity look compared to the displacement? It has the same direction. It's just, in my case, a third as big, okay? So if you always think about it like this, like the displacement is the change in your position, okay? It's the change in your position. It's the final position minus the initial position in terms of vectors. That's what displacement is. And then the velocity is the displacement over time. So it'll have to point in the direction of the displacement, but it won't be the same size because you're dividing it by a time scalar, whatever that happens to be. So here I could say, like, roughly to scale. I know this is not perfect, but the average velocity having to be a third as big as the displacement. There's the displacement. Right there is that average velocity, -1 and 2. It's going to point the same direction as the displacement. Just make sure you see why that is, okay? All right, so that's what I'll tell you about 5. So next thing, let's take this a little further, as would be the objective in going through the lesson, to keep taking it further. But let's say that we talked about average velocity, and the averages don't give us full information. It's kind of like if I tell you the average on the test in the class was a 75, that's very incomplete information. It doesn't tell you anything about anybody's particular score, okay? So like same thing with average velocity, okay? You see how this really can't tell you the whole story? If I say that's the displacement, do we really know that to get from here to there was exactly along that vector D? Like, we have no way to know that, okay? Now, I would think that the smaller the time increment was, the closer D would align itself to the actual path, though. All right? But if lots of time passes, it just gives the moving object time to deviate from whatever the displacement vector is calculated to be, okay? All right, so, here's what we're saying. There's the displacement vector, but we have no way to know whether that wasn't the actual path, okay? What I guarantee you, if you shrink this, if you make the time that's elapsed as small as possible, the direction of D will align itself with whatever the path is. And so it will be more accurate. And then since the velocity is derived from that, it will be more accurate too. Okay? So that's the short story on it. Now, anyway, so let's do like this. Let's say here's our basic framework. Initial position plus displacement equals final position. And there's basically that equation for the average velocity that I gave you already. Now, let's take this a little further and get a definition for instantaneous velocity. Let's say something like this. Here is r of t, meaning it's the position at time t, whatever that time is. And then here is r t plus h, which is the position at some later time. All right? Okay, now our displacement vector would still be this, okay? Because you take your initial position, you add your displacement, you get your final position. Now I say that's final because if this is your position at time t plus h would have to be a little later like say if we add h being a positive number. So all right, our instantaneous velocity as opposed to our average is still going to be the displacement over the time, but we're just going to let the time be pushed to 0. So we're going to say limit h goes to 0. All right. R t plus h minus r of t over h. H is how much time passed between initial and final, and then that's displacement. So it's no different than this. It's still displacement over time. It's just we want to push the time element to 0. Okay. All right, so that's the way that we do it. Now, so there's your definition of instantaneous velocity. Okay. Now let's do something to compare with this real quick. All right, so suppose we have an object that moves according to this. There's our position vector. Distances are measured in feet. Can you calculate the average velocity over this time interval? All right, now I could just refer you back to my equations. If I took this limit h goes to 0 out of it, that would be the average. If I have the limit as h goes to 0, that's the instantaneous. Okay, instantaneous, the velocity at any instant. All right, not over an interval of time, but at an instant of time. Okay. Anyway, all right. So sure, here's what it would be. Fairly simple math, I would say. That's the later time. Sorry, this is the initial time. That's a tad later. So we would want to do r of 1.6 minus r of pi over 2. Okay, that's the displacement. That's what the displacement will be, where I'm not going to draw it, but I'm just going to do that. Final versus initial, over the elapsed time, which is 1.6 minus pi over 2. All right, so now that would be subtracting vectors. So here's what I'll do. I'll calculate, I don't know, I don't think it's hard to calculate this. I'm going to pause the video, I'm going to calculate it, then it's going to show up all written down. So hold on just a second. Okay, so I did this, put 1.6 into r of t, put pi over 2 in, subtract the vectors, divide by this delta t, and that's what you're going to get. Okay? All right, so that's just a calculation of the average velocity, the way we had done it in another problem. Now, what is the instantaneous velocity at that instant? Okay, so I say instantaneous, there's the instant. It turns out that even though this might make it look complicated, and I guess sometimes we have to do it that way if we don't have any other options, v of t is pretty easy to find. It's just r prime t, which would be the term component-wise derivative of that. So we get minus 3 sine t and then cosine t. And say you found v at pi over 2, just like it says, we're going to get minus 3 and 0. You see how close those are? Okay, that's in feet per second. Yeah, they're close. Why are they close? They're close because this is